Non-regular languages pumping lemma. Pumping lemma is just a proof by contradiction technique where we need to prove that given language is not a regular language. If the language is regular, we will not use pumping lemma. We will use other proof technique which is called proof by construction. We will prove the language is regular using NFA, DFA, regular expression or regular grammar. But if language is not a regular language, then we can prove it by contradiction technique, and that's called pumping lemma. So non-regular languages, we know that the regular languages are those which are in the form of this technique: A star B. You have to any number of A followed by B. B star A, B star C, any number of B including the lambda followed by C, or A, only A. And here you can say B or C, but if there is a C, then C may or may not follow any combination of A, B star. If this type of languages are there and they are infinite, we say these are the regular languages. If the languages are not regular, which type of languages are not regular, like A and B N? In the A and B N, why they are not regular, we need to compare A and B in the form of they are must be exactly equal, because both have power n, and n means if there is a 1A, then there must be 1B. If there are 2A, then there must be 2B. So these type of comparison is not supported by the NFA or DFA because they don't have memory or stack. Similarly, VV reverse means V is a string and the reverse string is followed by the V string. So VV reverse means two string V and then opposite of that V. If there are A double B, then opposite of reverse of this will be double BA. So we need to capture that if A is coming first, then A must be coming last, and B is coming second and B must be at the second last position. So if this is comparison is required, that cannot be drawn with the NFA, DFA, regular expression or regular grammar. So how can we prove that language is not regular? We cannot say that there is no DFA, NFA or RE. It's a very nonsensible reason, nonsensible answer for that. We have to prove it, but this proving is not an easy task. So what we do, we apply the solution pumping lemma for that. Pumping lemma origin based on the concept of pigeonhole principle. If there are three pigeons and there are three pigeonhole and four pigeons, and we are storing one pigeon in the one pigeonhole, then we need to store or we need to keep two pigeons in the one pigeonhole. So it means there must be at least two pigeons in the one pigeonhole, at least one pigeonhole. If you are putting two pigeons here and two pigeons here, that might be empty, and we can say at least two pigeons in a single pigeonhole. The condition also satisfied. If there are n pigeons and m pigeonhole and n is greater than m, means number of pigeons are greater than the number of pigeonhole, then you have to put two pigeons in a one pigeonhole. It means repetition of pigeons will be at one pigeonhole. That apply on the DFA. When we map the same concept on the pigeonhole principle on the DFA, we say there are four states: Q1, Q2, Q3, Q4. If the string length is 3, we need two states for one string, one transition. On the A, Q1 to Q2, on B, Q2, Q3, and again B, Q2, Q3 to Q4. And if there is fourth symbol, last B, then we need to repeat that Q4 starting state is Q4 and ending state is also Q4. If there is A, then starting state is Q4 and ending state is Q3, and we are repeating Q3. So in such a way, if they are more than 4 or 4 equal to 4 or more than 4 number of characters, then we have to repeat at least one state. So here you can see, if there is a single A, double A, then no problem. If double A, B, no problem, because we are not repeating state, no state is repeated. But length of the string is greater than the 4 or equal to 4, then we need to repeat the state. So for string double A, B, how we have to assess, how to check on the DFA? A, and then B, and again B means loop. We have to execute the loop. Similarly for double B, so we have to repeat the state like the pigeonhole principle. So if W length is greater than or equal to 4, then we have to repeat the loop. Then the transition of string W are more than the states of the DFA, state must be repeated. So in generalized way, if we say W is a string and has the length which is greater than number of states, then any Q must be repeated. Any state must be repeated in the walk of W. So walk of W, here you can say, if W is a length equal to or greater than the number of states, there will be a loop. There will be that our cycle is showing that particular state is being repeated. Similar that we are using the pigeonhole principle. In other words, if we say the pigeon mapping to the transition and hole mapping to the state, so then there are two pigeon in a single pigeonhole. So pumping lemma, this is a pumping lemma. We say if we take infinite regular language, because the finite regular language is always a regular. So if the language is finite, this is always a regular. You don't need to check it. You can easily construct the DFA for that. But if there is an infinite regular language, the infinite means there must be cycles, otherwise not possible, because in a finite states, infinite strings can be accepted only if there is a cycle or loop, otherwise no. So there must be some state accept, but if the length is path will be followed and the loop will repeat that state. The loop will repeat. This is a cycle, and you have so that the infinite string can be processed on this path, and you can support an infinite language. Otherwise, no way to support infinite language. So taking a string W belongs to L. So taking, there is a label walk W, and we are performing the walk, but no loop, no cycle. It means W must be finite. If there is infinite, the loop is here. So if a string has a length W which is greater than or equal to number of state from the pigeonhole principle, the state must be repeated in W. There could be many state repeated, not necessarily one state can be repeated, and there are many state can be repeated, but at least one state must be repeated. So first state repeated in the walk W, we can use that repetition when we are designing that pumping lemma. We need to consider that repetition may be counted in the Y when we are splitting our string into XW, XY, Z. So that repetition will be the VY. So there is a path VW. We decompose W into the XYZ substrings. X substring is that where no repetition. Y is that particular path where the cycle or looping involved and Z is remaining part. So we decompose our W in such a way that first part without repetition X, last part without repetition Z, and Y is that part which is converting, involving the loop or cycle. So if there are X or any number of characters, sigma 1 to sigma I, Y are sigma to J, and Z is J plus 1 to K. So there are, we can say, n number of characters, there are m number of characters, there are Z, K number of characters, any number of characters can be in the substring X, Y, Z. So only when you are designing the infinite string, Y is involving to design infinite string, because Y is contributing towards increment of the length of string. So therefore Y should not equal to the lambda. Y will contain at least one character. It can be more than one, but at least one character. It cannot, the length of Y cannot be equal to 0. The length of Y should be greater than or equal to 1. So we put that condition or constraint on pumping lemma. And the length of xy must be less than m. This is another criteria, that length of x and y must be less than or equal to m. It cannot be greater than m, because when we are designing the pumping lemma, we take a string in which only y comes once. Either the string of that particular should be which involved only one loop at most. So here you can say x is without loop and y part is with loop or with cycle. The length of y should be greater than or equal to 1. It means we cannot store y as a lambda. The lambda cannot be stored in the y. It should be some character which contribute to the increment of the length of a string. Since there are at least one transition in the loop, and that transition cannot be lambda. So here you can say that if we are taking the other parts of string which involve the x and z, which is non-cyclic part or substrings, they can be used in string only once only, and z is once only. But y is that part that can be repeated. So the first string without loop can be xz, no loop involved. So you are just straightforward coming to q and then going forward. The minimum string can be xz without y, and the other string will be xyz, and then other string will be, next will be xyyz. So you have to increase y, number of y. So no loop, do not follow loop, only the xz. If you follow the loop, it means xy 2 times, 3 times. Here you can follow the loop 3 times, it means xyyz. And you can define the y can be repeated any number of times, because there is a loop and loop contributed to the infinite strings generation. So it can be 0, only x and z. It can be 1, xyz. It can be 2, x, y, y, z, x, y, 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 z, and so on. Then y can be y power I, any number, 0 to infinity. So if the strings have the pattern, so we say the string belongs to L, it means regular language. If the string does not belongs to L, means language is not regular. That's a pumping lemma. So pumping lemma have some conditions that I mentioned. The y cannot be lambda, y should be greater than or equal to, length of y should be greater than or equal to 1. The length of xy should be less than or equal to number of states. So these are minimum criteria. Y, length of y should be greater than or equal to 1, and length of xy should be greater than less than or equal to m. These are the two criteria. And what are xy? Xy are the substring of w. W can be decomposed into three substring x, y, z. So given an infinite regular language L, there exists an m an arbitrary number. For any string w belongs to L with the length, we can say the length of w is greater than or equal to m. M is showing the number of states, or we can say any arbitrary number that can be used to get the substring of xyz. We need to write string w into x first part without repetition, y loop, z last part without repetition. The length of x equal to m, and this is a logical and, means both conditions should be true. If any condition is false, then result will be false. You are not fulfilling the criteria of pumping lemma. So y is greater than or equal to 1, such that x, y, I, z belongs to L. If this is the pattern and you are increasing by the all strings generated from this pattern must belongs to language. And what does it mean I? I means I can be 0, I can be 1, I can be 2, 3, 4, 5 up to infinity. Now coming towards the application of pumping lemma, you have every language which is finite. You don't need to worry about it, just construct an FA for that or DFA for that. Finite language always will be regular. Therefore, non-regular language has to be infinite in size. If language is infinite, it can be regular, may not. So suppose that we want to prove that an infinite language L, which is not regular, we know that which is not regular, but we have to prove that it is not regular. For that we have to take assumption opposite, which is that L is a regular. The pumping lemma should hold for L. The pumping lemma can be applied on the L because we are saying that L is a regular, then for regularity checking, pumping lemma can be applicable. Use pumping lemma to obtain the contradiction. Therefore, L is not regular. Contradiction that pumping lemma is invalid or cannot be applied. If you apply the pumping lemma that generate a string w prime which is not belongs to L, it means it is a contradiction, then you can say L is a not regular. So explanation of step 3 in detail, how we can get contradiction. You have to take m length, critical length of L. Then choose a particular string w that belongs to L. And when you take w which belongs to L, you have to check that w must be greater than or equal. That's a requirement for pumping lemma. And w will be decomposed into three parts. And you have to devise or extract a string which is w prime, and that w prime, if you change the y 1, 2, 3, 4 any number, and you have a string that does not belongs to L for any, you can say, other than, because we have taken when I was 1, we have taken that string was part of the language, we have taken in this form. But if we change the y to 2, 3, 4 any number, and we have that it does not belongs to L, that's a contradiction. That's a contradiction, and the contradiction shows that given language is not a regular language. This gives a contradiction since w prime does equal to x, y, I, z belongs to L. It should be belongs to L, but actually we have an observation that it does not belongs to L, that gives a contradiction. So for contradiction we need to suffice that we show one string only. Any one string is sufficient to prove that the language is not regular. We don't need to find out many in the string for that. So example of pumping lemma, we take A and Bn. We know that this language is not regular, but we have to prove it. For proving, we use the pumping lemma. For pumping lemma, we know that for contradiction, that language we have to know assume that for the contradiction language is not language is regular. Since language is infinite, we can apply the pumping lemma. When we apply the pumping lemma, we pick a string W, we decompose the string into three parts x, y, z. So we take a string W, A, M, B, M. We know that A, N, B, N have some arbitrary number M. We take the M length A, M length B. Number of A are M, number of B are M. Both are equal. We take W. Then we decompose W into that three substring x, y, z. So x, y, z means y is that part which contains the loop. So am, bm, we take one part, any number of a in the x, any number of b in the y, and remaining number of a and b in the z. How to take these numbers? We have to take any number of a in the x, and how many y number of a can be in y? It should be greater than or equal to 1 and less than or equal to m. This is the criteria for k. The length of y will be a power k, or where k is between 1 to m. It can be 1, it can be 2, 3, 4, but maximum it cannot be more than m, the maximum length, because we know that the length of string we have taken m, and we know that the combination of x and y should be less than or equal to m. So if we take y greater than m, then this condition will be false. So we need to keep this condition. The y can be up to m if we take x as a lambda, but if we have some x more not lambda, then it must be less than m. So that's why we define that y is 1 to m. So now we apply am and bm, pumping lemma y power ak. The pumping lemma says that if we have a string which x, y, y, z, it also belongs to L, because pumping lemma says any string which is on that pattern, it should be belongs to L as a part of language. But if we take y, y 2 times, the length of y is k. So when we take a symbol string, it's a m, total length is m. But if we take y 2 times, then it length of y will be plus 2m. And then when it will be plus 2m, the length of y, this string will be, number of a will be m plus k, where the number of b are only b, m. So the length of a, or number of string, number of a in the first part will be increased by the k, where number of b are the only m. So we know that m is not a 0, k is not a 0. So if it is not a 0, it means this is not equal to this one. According to rule, the number of a's or number of b's are equal given in the language, because both length has n. So it, according to pattern of pumping lemma, it should belongs to L. But as we know that k is non-zero, it means the length of a's or number of a's are greater than the number of b's. It is not a contradiction. We know that this does not belongs to L, and that's a contradiction. And this contradiction shows that the language A and BN is not regular, non-regular language, NRL, non-regular language. So that's a proof, and a proof that we have taken a string and then pump it, then we find out the contradiction, and it's a L is a not a regular. Same can be tested on the second language, which are, so we can say non-regular A and Bn is a non-regular language. Similarly, we can construct proof for WW reverse. So WW reverse means if there is a string in the pattern A B, then reverse will be B A. If we have to follow that string following the pattern, then this string will be in the same fashion that belongs to L. L is a, if it is a L is a regular, then it must be following the pumping lemma constraints. So we check it for proof by contradiction, and this is the same process as in last example. We know that this is not regular, but we have to prove that this is not regular. We will decompose this string into the three parts x, y, z. As we know that it is infinite, we decompose the w into, we know w should be in such a pattern. If there is a am bm, then reverse will be bm am. So this string reverse is this one. So w can be decomposed into three parts, which are x, y, z, and we take x from a's, y from a's, and remaining a's can be, all the strings can be in z. So we have taken the y from a's, and y from a's has length k. K length means 1 to m. It is greater than or equal to m and less than or equal to, greater than or equal to 1 and less than or equal to m. So we know that x, y, z belongs to L. We know that this is true. Okay. Then x, y, z also belongs to L. If we substitute y square, then we know that number of a are k and will be increased by k. So number of a's will be increased by k, m plus k, where the number of a in the last part are m. So they are not equal. They should be same length, but they are not equal. So it means the string that is a power mk plus b into concatenated with the bm into bm am, then am and amk are not equal. It means this is not a reverse string. If this is not a reverse string, means it does not belongs to L. It should belongs to L, but it is not belonging to L. That's a contradiction. And that contradiction shows that the language is not a regular. So WW reverse is not a regular. That is